Hello students, this is a video on section 7.3, bonding in metals. The objectives we're covering: model the valence electrons and metal atoms, describe the arrangement of atoms in a metal, and explain the importance of alloys. So here we have a picture of a fence, and it's made with iron, pure iron, and a trace of carbon. So it's what we call an alloy. Metals have distinct properties, and it's due to the way the metal ions form bonds with one another. So in this section, we're going to talk about the metallic properties and metallic bonds. So in the last section, we talked about ionic compounds. The ionic compounds are metals and nonmetals, such as fluorine, chlorine, nitrogen, oxygen. Well, with pure metals, we're talking about metallic bonds. We're not having any anions in it. So metals are made up of closely packed cations, just the cations rather than neutral atoms. So here we have a picture of, we see the nucleus and we see these electrons. However, what we see here is these valence electrons. Notice these valence electrons are moving around. They are free to move around. So the valence electrons of the metal atoms can be modeled as what we call a sea of electrons. They are not stuck just with the atom, they're moving around. You know, they can be mobile. Okay, so these mobile electrons, and let me circle a few just so you can see a few of them here. These mobile electrons. So metallic bonds consist of the attraction of these free-floating valence electrons, and here we see them in this picture, for the positively charged metal ions. And these bonds are the forces of attractions that hold the metals together. Now you're probably thinking, okay, here we have these cations, these positive charge ions. They should repel each other. Well, you have these electrons. It's almost kind of like, think of ball bearings in oil, where the oil lubricates the ball bearings. So here we have these electrons that are attracted to the plus, and so the electrons are kind of in between all the cations here. So we have these free floating, and this on the left side shows a charge of +1, and so therefore for every cation here you have one electron floating around. Notice on the right side here, there's two separate examples, and probably I should draw a line here. On the right side here you see where you have a +2 charge. So now you have two valence electrons moving around. Let's say this might be a pure magnesium, where you'd have a +2 charge. And so it forms this kind of a buffer, and it holds the cations together, these mobile electrons. So some physical properties of metals. They're good conductors of electric current. The electrons can flow freely in them. So here is another picture where you see these electrons are flowing freely, and so then you can have another electron where electricity is a flow of electrons. So now you have these other electrons kind of slink their way through. Nobody really notices because you have the sea of electrons, these free-floating electrons. And so that's why metals can conduct electricity. These electrons can flow through the metal because there's other free-moving electrons. Some other properties of metals. Metals are ductile, meaning they can be drawn into wires. And so you can push a metal in and compact it, and it would be a wire. And also metals are malleable. Malleable means that it can be hammered or forced into shapes. And so here we see an example. We see the sea of electrons here. Those are the yellow. And we see the cations here. And when you push it, Okay, when you push these cations, they slide past each other because you have these electrons kind of in between. And so therefore cations don't come in contact with each other. You have the electrons kind of flowing in between, and so it can be pushed. And so that's why when you hit a metal, it can be hammered into let's say a flat piece of metal, or it can be, forced into shapes. It doesn't break into pieces like blocks of sodium chloride. So here, when a metal is subjected to pressure, the metal cations easily slide past one another. It's the same picture. So in here you can see this here. Let me just circle it. It can be, see how it can be pushed down, and so they slide past one another. And here we compare. So in this slide here, we're comparing metals and ionic compounds. We talked about ionic compounds in the last section. So here we have an ionic compound here, and when you push, add a force to it, now you have two negatives together, two positives together. Now these blue circles are the anions, the red are the cations. And so you have strong repulsions, and it breaks apart. And that's the ionic crystal. That's down here. On the left, you see a force. This force is pushing down, and you see it just slides past it with a metal. So they're not repelling because we have these free electrons here, a sea of electrons. So this shows you, compares metals and ionic compounds when a force is added. In an ionic crystal, we have the crystal shatters. In a metal, it can be formed into different shapes. So we have a crystalline structure. Metal atoms are arranged in very compact and orderly patterns. We have three types of closely packed arrangements. We have what we call body-centered cubic, face-centered cubic, and hexagonal close packing arrangement. And we'll look at some pictures of these. So in the body-centered, this example is a body-centered. And here on the right, you can see a diagram where you have a cube, and so each atom is at the corner of the cube, and then in the center of the cube, you have an atom. So it's called body-centered. This is the whole body, and this would be in the center. So every atom except those on the surface has 8 neighbors. Examples of body-centered cubic elements would be sodium, potassium, iron, and chromium. And tungsten, they crystallize into a body-centered cubic pattern like this. Here's a picture of chromium, and again, here's the diagram where it's body-centered. And here's another picture, a larger picture of body-centered cubic. Again, you have on each cube, each corner here, and then you have one on the center, in the center. The next is what we call face-centered cubic. Every atom has 12 neighbors. Copper, silver, gold, aluminum, and lead have this type of arrangement. And if you look at this, sometimes it's kind of hard to see. If we kind of look at one face, it almost looks like a 5 on a die. And then here, we have the center here on the face. So we have one here. This is just the face. 2, 3, 4, 5. Now it's like that on every face. And here's another one. Let's maybe do this in another color, where I could do this here, here. So this is what we call face-centered cubic. And so here we have, and let's color code this a little bit. So here we have 1, 2, 3, 4, 5. Okay, so each face is kind of like a dice, and it's like the number 5 on a dice. Each face has an atom in the center there, plus on the cube, on the corners of the cube. So this is called face-centered cubic. And here you can see an example. Again, here, if you look at the square here, and then this is on that face, it's a little easier to see maybe the top one here. Here we go here, here. And then here is in the center of the face there. And then here would be the side. It's kind of hard to see, think in 3D on two dimensions. Okay, so this is what we call face-centered cubic. And the last is hexagonal close-packed arrangement. Every atom has 12 neighbors. Patterns is different than the face-centered cubic arrangement. And examples would be magnesium, zinc, and cadmium. And if you look here, you see this pattern on the bottom, and then a pattern in the center, kind of sits in the center here, and then this pattern on top. It alternates with this 7 atoms, and then you have 3 atoms. So 7 atoms, 3 atoms, 7 atoms. And you see that this is called hexagonal close packed. And let's see if we have here's another example where you can see it, arrangement here. And it'd be on one on, top of the other, 7, then the 3 in the center, that B layer, and then this layer again, like this A layer. And here you can see it here in the center, and here. So for here is the hexagonal close packed, and these are just different types of pictures of the same thing. Here you can kind of see the hexagon shape here, 6 sides, and then one in the center there. So alloys. Alloys are mixtures of composed of 2 or more elements, at least one of which is a metal. They are important. Okay, we have alloys because their properties are superior than those of their component elements. A lot of times when you mix things together, it makes a better product than if they were by themselves, the metals by themselves. And we call this alloys. And we have a lot of alloys. Example, brass is an alloy. It's composed of copper and zinc. Sterling silver is an alloy. It's 92.5% silver and 7.5% copper. It's harder. If you had pure silver, it would be soft. So with a little bit of copper, it makes it harder and more durable than pure silver. And it's soft enough to make jewelry and tableware. Bronze, 7 parts copper, 1 part tin. So again, these are what we call alloys. They're more than one metal mixed together, and they usually have, they're more durable and they have better properties than the pure metals. Here's a couple examples, and here's the cast iron. Now some of you might have a cast iron, maybe your grandparents or a great aunt or something might have a cast iron frying pan, and that is iron and copper. Stainless steel, most of our tableware is stainless steel, and that's iron, chromium, carbon, and nickel. Okay, cast iron is iron, and they say copper, iron, and carbon, and here we have carbon here. Now, spring steel is a little different, doesn't have the nickel, and surgical steel. This has molybdenum. Okay, we have iron, chromium, nickel, and molybdenum in the surgical steel. So these are some common alloys, and you might be familiar with a few. So we have 2 types of alloys. So we have what we call substitutional alloy, and it has the word substitute in it. And what happens here is the atoms of the components in an alloy are about the same size, and they can replace each other in the crystal. So here we have a picture of a crystal here, and we have these blue circles, but we have other elements, and it's about the same size, so it kind of takes the place of an atom of the pure metal. You see, it takes the place. That's why it's called substitutional. Okay, it's about the same size, and they can replace the metal in the crystal. Here's another picture with marbles. Again, instead of having a green marble, we have these purple marbles here. So if the atoms are about the same size, we get that substitutional alloy. One kind just takes the place of another kind of atom. Okay, so it just takes the place of another type. The network remains more or less the same. So you still have the same pattern, and one just substitutes in for something else. The interstitial alloy, the atomic sizes are very different. The smaller atoms, so here you can see the larger atoms, these blue, and then there's very small spaces, and in between you have other atoms stuck in there. So you have the atomic size are different. The smaller atoms can fit in the spaces between these larger atoms. An example, steel would be like this. You would have larger atoms and then smaller atoms stuck in here. And here's another picture with the marbles. Now here you have the same pattern and you have that space. Here you can kind of see the space, not really that well in this picture here. But here you can kind of see that where the space would be, and that's where those other white beads kind of stick in between the marbles. So if added, the atoms are much smaller than the atoms in the network. And this is the green marbles would be the atoms in the network. So like carbon atoms added to iron to make steel, they can fit in the holes. And just look at on the periodic table of the atomic number of iron, it's much larger than carbon. Carbon has atomic number of 6, and iron has somewhere in the 50s, I think. So it's much larger. Okay, so this is a short section. Closures comments here. The valence electrons of metal atoms can be modeled as a sea of electrons. Metal atoms are arranged in very compact and orderly patterns, and alloys are important because their properties are often more superior than those of their component elements. The homework assignment is to read section 7.3, pages 201 through 203.